Chapter 1 Valence Bond Theory VBT. Contents: Lewis structures, valence shell electron pair repulsion theory VSEPR, valence bond theory, and orbital hybridization. Learning outcomes: at the end of this lesson, students should be able to construct and sketch the geometry of molecules of polyatomic ions based on Lewis structure, valence shell electron pair repulsion theory VSEPR, and valence bond theory. Lewis structures: molecular formulatron with Lewis symbols, method for diagramming electronic structure of covalent bonds, use dots to represent electrons, covalent bond shared pair of electrons. Each atom shared electrons so has complete octet 8 electrons. Noble gas electron configuration except hydrogen, which has complete shell with 2 electrons. Lewis symbols: write chemical symbols surrounded by dots for each electron. So when you look at the group number 1A, 2A, 3A, and 4A, so here the valence electron for the hydrogen is equal to 1. And we look at the helium has 2 valence electron, so equal with the group number. And same here with the beryllium and also the magnesium. So next is the group 5 to 8. So this is the electron configuration, and the valence electron followed the group number. Look at the nitrogen here, has 5 valence electron. So the group number is equal with the number of valence electron. Lewis structures: many nonmetals form more than one covalent bond. Look at the carbon, needs 4 electrons to form 4 bonds. And for the nitrogen, needs 3 electrons to form 3 bonds, while oxygen needs 2 electrons to form 2 bonds. So this is the example of methane. I have the for methane, look at this is the 4 single bond. And for the nitrogen, here bond to the hydrogen, 3 hydrogen. So this is the ammonia, and this is the lone pair. And this is the oxygen, bond to the 2 single bond of hydrogen, and they have a 2 lone pair. So this is the water molecules. Drawing Lewis structures: not all molecules obey the octet rule. Holds rigorously for second row elements like carbon, nitrogen, oxygen, and fluorine. Boron and beryllium sometimes have less than octet. For example, beryllium chloride and also the boron chloride. Second row can never have more than 8 electrons. Third row and below atoms often exceed octet. So you know the octet is the 8 electrons. Why? This is because N is equal to the 3 shell can have up to 18 electrons, as now have d orbitals in valence shell. Method for drawing Lewis structure: first, decide how atoms are bonded. For example, we look at this SiF4, silicon, fluoride, skeletal structure, arrangement of atoms. So this is the skeletal structure. We have the silicon 1 and fluorine, have a 4 fluorine here, and central atom is the silicon. And when you look at the count, all valence electron, all atoms, we count it. We look at the silicon, one silicon, and they will have the 1 times 4 because the silicon is group 4. If group 4, meaning that equal with 4 valence electron. So this is the 4 electrons. So for fluorine, fluorine is a group 7. So meaning that 7 electron you times with 4. And the answer is 28. You total up this one, you get the 32 electron. So the single bond consists of 2 electrons and the balance is 24. So the 24 is the fluorine lone pairs. Place 2 electrons between each pair of atom and draw in single bonds. So this is the example. Look at this. This is the example. And the number 4, complete octets of terminal atoms. Atom attached to central atom by adding electrons in pairs. Place any remaining electrons on central atom in pairs. If central atom does not have octet, form double bonds. If necessary, form triple bonds. And the last one, calculate the formal charge. This is the complete terminal atoms. So this is the octet for the silicon, also for the fluorine. And try this exercise. We look at the VSEPR theory, valence shell electron pair repulsion, simple model using the electron domain concept, simple theory for predicting shape of molecules. A pair of electrons on the central atom occupies a position in space as to minimize electron pair repulsion. 2 types of electron domains. First, bonding domains. Electron pairs involved in bonds between 2 atoms. Non-bonding domains, electron pairs associated with single atom, meaning that this is the lone pair. All electrons in single, double, or triple bond considered to be in the same electron domain, we consider as 1. This is the summary VSEPR and hybridization table. You look at this electron domain. So for example, electron domain 2. So this is the EDG, electron domain geometry, linear. Predicted bond angle, and this is the hybridization of central atom is the sp because electron domain is 2. So for example here 1 2, so meaning that this is the sp 1 2. So when you look at the example of electron domains of 3, so this is the trigonal planar because this one have a 1 2 and 3. So the molecular geometry is the trigonal planar if don't have the lone pair. VSEPR theory is a bond between 2 atoms formed when pair of electrons with pair opposite spins is shared by 2 overlapping atomic orbitals. Sigma bonds head-on overlap of orbitals concentrate electron density concentrated most heavily between nuclei of 2 atoms, lie along imaginary line joining their nuclei. We look at the orbitals. So this is the s and s orbitals, and this one the p orbitals. This is the hybrid orbitals of the sp and sp. Pi bonds Sideways overlap of unhybridized p orbitals, electron density divided into two regions, lie on opposite sides of imaginary line connecting two atoms, electron density above and below sigma bond. No electron density along sigma bond axis. Pi bond consists of both regions equal with one pi bond. Can never occur alone, must have sigma bond, can form from unhybridized p orbitals on adjacent atoms after forming sigma bonds. Pi bonds allow atoms to form double and triple bonds. So this is the types of bond, sigma and pi bond. Look at the sigma is the single bond, and for the pi is a double and triple bond. And look at this, overlapping of s and p orbital for the sigma bond and overlapping of 2p orbital is pi bond. Look at the carbon to carbon is the one sigma bond, and for the double bond, so double meaning they have two, one sigma and one pi bond. If the triple, so you just remember 2 pi, and you have the plus 1 is equal to 3 for the triple bond. And how many sigma and pi bond are there? Look at this. So you remember for the triple bond consists of the 2 pi and 1 sigma. And for the single bond consists of the 1 sigma. Another one is the 1 sigma. So total is the 3 sigma bonds and 2 pi. Hybridization, mixing of atomic orbitals to allow formation of bonds that have realistic bond angles. Realistic description of bonds often requires combining or blending two or more atomic orbitals. Hybridization just rearranging of electron probabilities. Why do it? To get maximum possible overlap and the best, which is a strongest bond form. Blended orbitals result from hybridization process. Hybrid orbitals have new shape, new directional properties, and each hybrid orbitals combines properties of parent atomic orbitals. Hybrid orbitals. For the hybrid sp, the atomic orbitals use s and p. The electron geometry is linear. For the sp2, the atomic orbital is 1s and 2p, which is the electron geometry is trigonal planar. For the sp3, the atomic orbitals use 1s and 3p. The electron geometry is tetrahedral. So for the sp3d, meaning that this one have a 5 electron domain, so 1s, 3p, and 1d. The electron geometry is trigonal bipyramidal. For the sp3d2, the electron domain is 6, which is the atomic orbitals use 1s, 3p, and 2d. The electron geometry is octahedral. Now we look at the sp hybridization, which is the 1s and 1p orbital are mixed. Example, beryllium hydride, which is the electron geometry is linear. And for the electron configuration of beryllium, 1s2 to s2. So this is the Lewis structure. Now this is how you draw the energy level for the isolated beryllium atom and the hybridized beryllium atom. Now we look at the 2s2 here. So here is the 2s, have the 2 electrons, and for the p orbital is empty. And when mixed for the 1s and 1p here, become the sp, have a 2 orbitals, which is the 1s and 1p are mixed. So here 1 electron will jump to this 2p and they mix the orbital, become the sp for the hybrid orbitals of beryllium hydride. So this is the empty for the 2p. So we know the hydrogen here 1 electron, another for the hydrogen. So meaning that total up is 2 electrons. So this is the 1 electron for the hydrogen will go here and another one here will go to this orbital. sp2 hybridization. So this is the 1s and 2p orbital are mixed, become sp2. For example, boron chloride. This is the geometry trigonal planar. Electron configuration of boron 1s2 2s2 2p1. Electron configuration of boron 1s2 2s2 2p1. The proton number of boron is 5. So this is the atom. So the proton number is equal to the electron. So now we draw the 2s here, 2 electron, and 2p1, 1 electron. So we know this is the 3 sigma bonds. So this is only the skeleton of the BCl3. When you complete the Lewis structure, make sure you draw the lone pair of the chlorine. So this is incomplete for the Lewis structure, but this just show you the roughly of the BCl structure. So this is the 3 sigma bond. So we know when the 3 sigma bond, meaning that you must have the 3 electron here. So now here we look at the 2s, the 1 electron from the 2s will jump to this orbital, empty orbital for the 2p and mix, become 1s here and 2p here, so become the sp2. sp3 hybridization, 1s and 3p orbital are mixed. sp3 hybridization, 1s and 3p orbital are mixed. This is the example methane. The geometry is tetrahedral. Electron configuration of carbon 1s2 2s2 2p2. So this is the level of the energy for the isolated carbon atom. So this is the 2s2 and 2p2. So we know for the p orbital has a 3, and when mixed, because 1 electron here will go to this 2p, and when mixed become the sp3. So we know this is the 4 sigma bond. For the sp3d hybridization, the 1s and 3p orbital and 1d orbital are mixed. Example, BCl5. The geometry is trigonal bipyramidal. Electron configuration of phosphorus 1s2 2s2 2p6 3s2 3p3. This is the Lewis structure of the BCl5, consists of the 5 single bond, which is equal to the 5 sigma bond. So we know must have the 5. Okay, so 5 electrons here in the hybridized p atom. So here 3s2 follow this electron configuration, and 3p3, and 1 electron from the 3s go to here 3d, and hybridized p atom is sp3d. And for the sp3d2 hybridization, 1s 3p orbital and 2d orbital are mixed. Example, SF6. So the geometry octahedral. Electron configuration of sulfur 1s2 2s2 2p6 3s2 and 3p4. So this is the orbital diagram For the isolated sulfur atom, 3s2 and 3p4, and the pair of electron here for the 3s and 3p. So one electron go to this empty 3d and another one here and mix up become 6sp3d2. So because they have the 6 sigma bond. And lone pair example ammonia, electron configuration of nitrogen 1s2 to s2 to p3. This is the orbital diagram for the isolated and hybridized nitrogen atom. For the isolated nitrogen atom, follow the electron configuration, and when mix up all this one become the sp3. So why 2 electron here? Because this is the lone pair. When you look at the ammonia structure, consists of 3 sigma bond and 1 lone pair. So this is the hybridization, which is the sp3. Lone pair electron example for water molecule, electron configuration of oxygen 1s2 to s2 to p4. So this is the isolated orbital diagram for oxygen atom. When mix up all this one, 2 orbitals here are lone pairs and the rest is the bonding electron for the sigma bond. So the hybridization is sp3 because the water molecule has 2 lone pairs and 2 sigma bond. Double bond example ethane C2H4, electron configuration of carbon 1s2 to s2 to p2. So this is the Lewis structure. So this is like a mirror image. So we consider as C1 here and this is C2. So for the C1 consists of the 3 sigma bond and 1 pi bond, because the double bond here consists of the 1 sigma and 1 pi. Since there are 3 sigma bond and 1 pi bond, thus it needs 4 unpaired electrons. So this is the orbital diagram of isolated carbon atom. And when hybrid, 1 electron jump to here and become the sp2 for the sigma bond, 3 sigma bond and 1 pi bond here for the 2p. So only sigma bond consider as the hybridization. Triple bond example C2H2. So this is also the mirror image for the carbon 1 and carbon 2. So for the triple bond here consists of the 2 pi and 1 sigma, and another 1 sigma is the single bond here. So this is the electron configuration of carbon, and this is the orbital diagram of isolated carbon atom. When hybrid, so the split become this one sp for the 2 sigma bond and another 2 pi bond still in the 2p. Try this. Identify the HCN hybrid orbital. We done chapter 1. Thank you.